All right, today we are diving deep into one of the most powerful and, let's be honest, controversial elements out there, uranium. We're going to unlock the secret of its most potent form, uranium-235, and really get to the bottom of what makes it able to both power our cities and threaten them. I mean, you hear about it in the news all the time, right? Geopolitical tensions, nuclear programs, all these global treaties. But what is it about this one element that puts it smack in the center of so much debate? Why uranium? The periodic table has 118 known elements. But for some reason, uranium holds this unique power over world affairs. To figure out why, we've got to understand what makes it tick, atomically speaking. It all starts with this number, 92. Every single atom of uranium has exactly 92 protons in its nucleus. That's its atomic identity card, you could say. And it makes uranium the heaviest element that occurs naturally right here on Earth. Anything heavier? That stuff has to be cooked up in a lab.
Okay, but here is where it gets really interesting. When you dig uranium ore out of the ground, it's not just one thing. You're actually holding a mix of different versions of uranium, all kind of jumbled together.
So let's meet the family. And to really understand the different members, we need to get our heads around one key scientific idea. And that idea is isotopes. Just think of them as siblings. They're all part of the uranium family because they all have those 92 protons. But they differ in the number of neutrons they have, and that changes their weight and, more importantly, their behavior. So this table shows you the two main characters in our story, uranium-238 and uranium-235. Now, look closely. U-235 has just 3 fewer neutrons. It seems like such a tiny difference, right? But that small change, it's everything. With fewer neutrons acting as like a nuclear glue, the U-235 nucleus is way less stable. It makes U-238 relatively calm, while U-235 is fissile, which basically means it's just perfectly primed to split apart.
And that brings us right to the core question. Why is this one specific isotope, uranium-235, the key to unlocking such an incredible amount of power? What is its secret?
Well, the answer lies in this beautiful and kind of terrifying piece of physics known as the chain reaction. This is where all the magic and all the danger really happens. So picture this, a single free-roaming neutron. Since it doesn't have an electrical charge, it can just sail right past an atom's defenses and smack right into the nucleus of a U-235 atom, splitting it in two. And that process is called nuclear fission. Now, when that nucleus splits, the two new, smaller atoms, they don't quite add up to the mass of the original. So where did that missing mass go? Well, Einstein gave us the answer. That tiny bit of lost mass, the M, gets converted into a huge amount of energy, the E.
But just releasing energy from one single atom isn't the whole story. The real secret, the crucial part, lies in what happens next, something U-235 does that its stable sibling, U-238, simply can't do.
Think of it like a prison break. One neutron breaks out the first U-235 inmate. But in the process, it doesn't just release energy, it also frees 2 or 3 brand new neutrons. Each of those new neutrons then goes on to break out more U-235 inmates. And each of those releases more neutrons, and on and on and on. It's an exponential, self-sustaining cascade.
And that chain reaction, happening in a fraction of a second, unleashes a truly staggering amount of energy. It's the exact same process that can generate clean electricity for millions or be harnessed into a weapon of unimaginable destruction. But there is a catch.
And the catch is this, that superstar isotope U-235 is incredibly rare. For every 1,000 uranium atoms you find in natural ore, only about 7 of them are the U-235 we need. The other 99.3% is mostly that stable U-238, which just kind of gets in the way of a chain reaction. So if you want to use U-235, you've got to solve this rarity problem. You have to find a way to increase its concentration. And this is where we get to that controversial word you're always hearing in the news, enrichment. Enrichment is just the, admittedly, very difficult industrial process of sifting through all those uranium atoms to pull out more of the valuable U-235 and get rid of some of the U-238. It's a lot like panning for gold, but you're doing it on an atomic scale. But you can't sift a solid rock, right? So the very first step is to convert the solid uranium ore into a gas, specifically a compound called uranium hexafluoride. This lets the individual atoms move around freely so they can actually be separated.
The most common way to do this is with a machine called a centrifuge. It spins that uranium gas at incredible speeds. And just like when you're on a merry-go-round, the slightly heavier U-238 gets flung out towards the wall, while the slightly lighter U-235 tends to hang out closer to the center. So then you just siphon off that gas from the center, which is now a little bit more enriched with U-235.
And this brings us full circle, because by controlling this enrichment process, you can determine exactly what that uranium is going to be used for. See, the level of enrichment determines everything. To run a nuclear power plant, you only need uranium enriched to about 5% U-235. For powering things like submarines or aircraft carriers, that number jumps to around 20%. But to create a nuclear weapon, you have to push that enrichment level all the way past 90%. And this, right here, is the core of the whole global controversy. It's the same basic element, and it's the same fundamental process of enrichment. The only difference is the degree to which you do it. And that degree determines whether you're creating peaceful energy or a devastating weapon. The science itself is neutral. It's just physics, right? But its application? Well, that's a human choice. So the question that's left is, what ultimately decides whether a discovery like this is used to build our world up or to break it down?